Hi. In this video, we are going to begin our series on functional equations. So in the next few videos, I'm going to talk about the different things that you need to know to tackle Olympiad problems on functional equations. We will cover the theory and also the problem solving techniques that are required for this topic. And we'll do that through a lot of examples. So there will be a lot of examples explaining the concepts, and later we'll tackle tougher problems in functional equations so that you are well prepared for the Olympiads, right? So let's begin. And this is a typical functional equation problem. So this is how it looks like. Find all functions from R to R such that f of x plus x times f of 1 minus x is equal to x for all x belonging to reals. So this is a pretty simple problem. So we'll start off with easy ones and then we'll graduate to more difficult problems. So we want to find the set of all functions defined over the domain of real numbers and going to the codomain of real numbers, which satisfy this condition, right? So now whenever you have a situation like this, where you have f of x and some other f of something else, right? One strategy that you should always keep in mind is you can try to solve a system of equations and solve for f of x if possible, right? So for example, for any a, where a is a real number, you can put x is equal to a in this equation and get f of a plus a times f of 1 minus a is equal to a. This becomes our first equation. And notice that you have variables like this. F of a is a variable and f of 1 minus a is a variable. These are unknowns for us right now, right? So it would be nice if we had another equation that connects these two unknowns and helps us find these unknowns, right? So how can we do that? We can use the same relation since it is valid for all x being real. We can say put x is equal to 1 minus a in the same equation, and you will get f of 1 minus a plus 1 minus a into f of a, because 1 minus 1 minus a becomes f of a, is equal to 1 minus a. And this becomes our second equation. And now with these two equations, think of f of a and f of 1 minus a as your unknowns and just solve the system of equations to find f of a, right? It is very easy to solve this system of equations. You need to eliminate f of 1 minus a. So what I would do is multiply the second equation here by a and subtract it from the first equation. If you do a little bit of algebra, you will end up with this situation: 1 minus a times 1 minus a, f of a is equal to a square, which implies f of a is equal to a square over 1 minus a plus a square. Now you can also verify whether this equation or this f of x satisfies the original conditions or not. When you do that, you will see that it does satisfy the original conditions, and therefore this is the solution for this functional equation. So this gives us a initial idea that one strategy in solving functional equations is to try to get several equations involving your functional quantities and solve for them. So here we had two equations and two unknowns. Our unknowns were f of a and f of 1 minus a, and we solved for them to find the answer, right? Okay, let's look at another problem. This problem goes like this. Find all functions f from R to R such that f of x minus y is equal to f of x plus f of y minus 2xy for all xy being real numbers, right? Okay, great. So again, we'll try to employ the same method. We are going to try to solve for f of a in some way, right? So for any x is equal to y is equal to a, if you put x and y as a, you will get f of 0 is equal to 2f of a minus 2a square, right? So this is my equation 1. Now remember, here you can easily solve for f of a here, and that is simply f of 0 plus 2a square divided by 2. So all we need is the value of f of 0, right? All we need is the value of f of 0, and then we'll know what f of a is. So how can we find f of 0? It is actually pretty simple. Put x is equal to y is equal to 0 in the original equation. You get f of 0 is equal to 2f of 0 minus 0, which implies f of 0 is equal to 2f of 0, or f of 0 is equal to 0. And putting that value in this equation, we get f of a is equal to 2a squared over 2, which is equal to a squared. And you can check that this function f of x is equal to x squared definitely satisfies the original condition, right? So that is a solution. This was also a pretty easy equation to solve. All you needed was to figure out how to get f of a, right? You put some values and test out and find out f of 0. So another thing to remember is many functional equations, you will need to know the value of f of 0. That's a pretty common thing to try to find out, right? Let's look at a slightly more complicated function. This is the situation. Determine all functions f go from R to R such that f of x plus y plus f of x times f of y is equal to x square y square plus 2xy for all xy belonging to real, right? Okay. So we start off this problem by trying to find the value of f of 0. So let's start with put y is equal to 0 here and see what happens with this equation. You get f of x plus f of x times f of 0. And when you put y is equal to 0, the right hand side becomes 0. So this implies that f of x into 1 plus f of 0 is equal to 0. So automatically this tells us that there is a solution which is a trivial solution where f of x can be 0. If f of x is a constant function and is 0, then automatically that will satisfy this equation, right? Does it satisfy this equation actually? It doesn't, because the left hand side will always be 0, but the right hand side can be any other real number, right? So f of x is equal to 0 is not a solution. A constant function will not satisfy this functional equation because the right hand side can vary with different x and y, whereas the left hand side will always be a constant 0, right? So therefore that implies that this part cannot be 0. Therefore this must be 0. So you get f of 0 is equal to minus 1. So that is the first piece of information that we have got, right? Now let's try to go ahead, and now we try different values. Put x and y as a and a. If you do that, you will end up with this situation: f of 2a plus f of a square is equal to a power 4 plus 2a square. So this is my first equation. Notice that in my first equation only I have two variables, two unknowns, f of a and f of 2a, right? This is my first equation. I need to get another equation involving f of 2a somehow, right? Because then only I'll be able to solve them for f of a and f of 2a, right? So let's me do it on the next screen. My first equation is this: f of 2a plus f of a whole square is equal to a power 4 plus 2a square. The second equation will be obtained if I do x and y as a and minus a into the original equation, and I will get f of 0 plus f of a times f of minus a is equal to minus a power 4 minus 2a square. Now f of 0 was minus 1. So this equation is f of a into f of a minus 1 is equal to a power 4 minus 2a square, right? So if you bring the minus 1 to the other side, you will realize this is f of a into f of minus a is equal to a square minus 1 whole square. So this is my second equation. Now notice that the first equation had the variables f of 2a and f of a. This equation has f of a and f of minus a. So technically I have increased the number of variables to 3 now. I have f of 2a and f of minus a. So I need another equation which can connect f of 2a or f of minus a, right? So now I'll take x and y as 2a and minus a. And in that case, the thing becomes f of a plus f of 2a into f of minus a is equal to 4a power 4 minus 2a square. So now this becomes my third equation. This is my second equation, and this was my first equation, right? So with these three equations, you have a simple situation now where this is an algebraic problem with three unknowns. You can call f of 2a, f of a, and f of minus a as x, y, z and solve for f of a, right? Or you can notice that if you look carefully, the function that clearly satisfies this is f of a is equal to a square minus 1. That function will satisfy all of these conditions because notice here a square minus 1 and a square minus 1 is becoming this, and you can check whether it verifies all the three conditions or not. The other way is to simply solve these three equations and try to find f of a. How will we do that? By eliminating f of 2a and eliminating f of minus a from these two equations. So again, this was a problem where we needed to solve a system of equations to find our answer, right? Let's move on to the next problem. Question 4. We have find all functions f from R to R which satisfying for all reals x and y mod of x times f of y plus y times f of x is equal to f of xy plus f of x square plus f of y, right? This is the situation. Okay, so we start off by taking some values, put x and y as 1 and 1. If you do that, what will come? F of 1 plus f of 1 is equal to f of 1 plus f of 1 plus f of 1, right? Which implies that clearly f of 1 is 0. That's the first thing that we get. Now, if you do x and y as 0 and 1, what will happen? This will vanish and you will get 1 time f of 0 is equal to f of 0 plus f of 0 plus f of 1, right? And now we know f of 1 is 0. And from here we get f of 0 is 0 basically. This is the second fact that we know from here, right? Okay. Now notice that there is a f of x squared term here. So I don't want to put x is equal to a. I want to put x is equal to root a, right? So what I will do is xy is root a times and 0. Why? Because that will make it f of a here, right? So what I get here is root a times f of 0 plus y is 0. So second term vanishes is equal to f of 0 plus f of a plus f of 0, right? We already know that f of 0 is 0. So this vanishes, this vanishes. And we are getting f of a plus f of 0 is equal to 0, right? So let's rewrite this last step here. We get x and y when we put root a and 0. We are getting this equation f of a plus f of 0 is equal to 0, right? And so far before this, what have we found? We have found f of 0 as 0. And we have found f of 1 as 0 as well, right? These were the two other pieces of information that we got earlier, right? Now, this equation, when I put x is equal to root a, obviously this is valid for all a greater than equal to 0. Because then only x will be a real number and the equation was defined for reals, right? So this equation is valid for all a greater than equal to 0. So that means f of 1 plus this is 0, f of 2 plus this is 0. So let's choose a specific a. Choose a specific a. Which a? A is equal to 0. So then we can put that here and we get f of 0 plus f of 0 is 0. But f of 0 is 0. So therefore this is also 0. So what we have gotten is f of 0 is also 0. Right? And this also tells us that now f of a plus 0 is 0 for all a greater than equal to 0. So we know a lot of information about the function now, that f of a is 0 for all a greater than equal to 0. This is something that we have figured out now, right? Great. Now let's say that b is a real number, and now we will put x and y to be equal to 0 comma b, right? X and y is 0 comma b. So in that case, the first term will vanish and you will have b f of 0 is equal to f of 0 plus f of x square is 0 plus f of y was b, right? So we are getting this, and f of 0 is already 0. So all of these terms are vanishing, and we are getting basically f of b is 0 for all real b. Notice that that's why we got two of these as 0, right? So we have proved that f of b is 0 for all real b, right? Great. So notice what information we have. We have f of 0 is 0, this is 0, this is 0, this is 0 for all real b, and f of a is 0 for all a which are positive, right? Now only thing to consider is the negative values. So let c less than 0. Now at x is equal to c, if I put x is equal to c in the original equation, I get mod c f of y plus y times f of c is equal to f of cy plus f of c square plus f of c, right? Now remember what all we have found out about the function. F of c is always 0 for any real number, right? F of c square, think about it. We proved that f of a is equal to 0 for a greater than equal to 0. So even if c is negative, c square is positive. So this is going to vanish, right? F of cy we don't know because we don't know the value of y. Mod of c can be written mod of c f of y. Okay, so our condition is becoming these two terms are gone. We have mod of c f of y plus y f of c is equal to f of cy. This is the situation for any negative c, right? Now we put y is equal to minus 1 in this. We get mod of c f of minus 1 plus minus 1 into f of c is equal to f of minus c. Now think about it. If c was negative, minus c is greater than 0. So this term is going to vanish. So this is going to be 0. And now what we can say is mod of c f of minus 1 minus f of c is equal to 0. Now mod of c can be written as what? Since c is less than 0, mod c is equal to minus c. So we can write it as minus c f of minus 1 minus f of c is equal to 0, which tells us that f of c is equal to minus f of minus 1 times c, right? So this gives us a condition for c negative. We are getting an equation which solves the problem because we are getting the condition on f of c for c negative. So our function overall is becoming f of x is equal to 0 for x greater than equal to 0, and it is equal to minus f of minus 1 into x for x less than 0. So a lot of things were substituted in the original functional equation. And once we do all of that, we slowly build up information for the problem. So you have seen that we started off with very easy equations, right? And afterwards, we were looking at more and more complicated systems, and we are putting in more and more information and slowly deriving the properties of the function. So that is the general strategy. You cannot have a set way to approach these kinds of problems because every problem is different and it requires a little bit of creativity. So what I would recommend is for you to try and tinker around with different values and try to figure out more and more information in a step-by-step manner. And that is a strategy that often works with functional equation problems, right? However, we need to develop some more tools and know some more theory before we approach slightly more complex problems. So the first things that we will discuss as part of our theory is the theory of injection, surjection, and bijection. These are basically types of functions. So let's try to understand all of these types of functions. So what is an surjective function? So surjective function is basically an onto function, a function where the range is equal to the codomain. So the condition is the range is equal to codomain for a surjective function, right? So basically the way we write it is f is a function from a to b. Here this is the domain and this is the codomain. Now this function is surjective if for any b belonging to the set B, if for any b belonging to the codomain, there is some a belonging to the domain such that f of a is equal to b. So basically we are saying that every element in the codomain is definitely having a pre-image in the domain. Or another way of saying that is range is equal to codomain, right? So that is the meaning of injective function. The second type of function that we'll talk, that is the meaning of surjective function. I made a mistake by saying injective. That's a surjection or an onto function. Next, we look at the definition of an injective function. So what is an injective function? So this is basically a 1-1 function. So what this means is if f of a1 is equal to f of a2, that implies that a1 is equal to a2. What this means is you cannot have multiple elements in the domain linking to the same output in the codomain. This is not possible. This is a many-to-one function, right? So as soon as you know that the outputs are equal, you are guaranteed that the inputs are also equal. F of a1 is equal to f of a2 should imply that a1 is equal to a2. That is the definition of an injective function. And lastly, we look at what is a bijection. A bijection is basically a 1-1 plus onto function. So what this means is it is both injective and surjective. Both injective and surjective. That is the definition of a bijection. You will also learn later that bijective functions are also invertible. They have inverses, right? Let's look at a simple problem. This problem says let f go from R to R and f satisfies this condition, f of x, f of y minus f of x is equal to 2f of x plus xy. This is true for all xy belonging to real, right? We have to prove that this function is surjective. Any function satisfying this relation is going to be surjective, right? So basically what we have to prove is that for any b belonging to real, there is an a belonging to real such that f of a is equal to b, right? So if you look at the original equation and in this you put x is equal to 1 and keep y as y itself, right? So this will become f of y minus f of 1 is equal to 2 times f of 1 plus y, right? And this is true for all y belonging to real, right? This relationship will be true for all y belonging to real. So now consider b as a real number. And what we will do is if we choose 2f of 1, the right hand side of this equation, 2f of 1 plus y is equal to b. In that case, we will get f of something is equal to b, right? So for any b is equal to real number, we can say that b is this. So basically we are saying y is equal to b minus 2f of 1, right? And in that case, the condition that you're getting is f of y minus f of 1 is equal to 2f of 1 plus y. We are calling this part as b. So basically we are saying that y is equal to b minus 2f of 1. And what we are saying is that this part becomes my a, right? So we have the condition f of a is equal to b. So whenever we choose y as this, my a becomes what? F of y minus f of 1, right? So what is y here? We can put a is equal to f of, instead of y, we can put b minus 2f of 1 minus f of 1. So what we are getting is from the definition of the functional equation itself, whenever you choose a y value or a b value, right? That b value can be written in terms of this y. Y is b minus 2f of 1. Then the a value that is coming, the input value is always going to be this, f of y minus f of 1, where you can remove the y again and you're getting this. So it always satisfies f of a is equal to b for any b belonging to real. Now notice that this equation was true for all real y's, right? So even if you wanted to take any particular b, let's say b was 101, right? So b was 101, then automatically you will be able to find a y such that this b is going to be 101, right? It is the y value is simply 101 minus 2f of 1, right? Once you know the y value, you can always find the a value and you can always find the input which will give us f of a is equal to b. So by using the functional equation cleverly, we are able to figure out that this will always be surjective, right? So that is the proof that this is surjective. In the next video in the course, we are going to look at all of these conditions of injection and surjection in more detail, and we'll solve more problems on these types of situations, right? So stay tuned for more videos in this series. This is just the starting point of our course. There are going to be plenty more videos where we discuss concepts and also a lot more Olympiad problems and harder problems. This is just the beginning of the course. I hope that you enjoyed from the video and learned a lot from this, and stay tuned for the follow-up videos. Please do like the video if you like the content and subscribe to the channel if you haven't already done so. Also, please make sure that you turn on notifications so that you are aware when the next video is being put up and you can follow it along, right? That's it for this video. I'll see you next time.